Have you ever wondered how quantum tunneling works? A fascinating phenomenon of the quantum world. Quantum tunneling sees particles, like electrons, straddling the line between particles and waves in a display of wave-particle duality. Imagine these particles approaching an energy barrier. Unlike the classical world where a lack of sufficient energy would halt their progress, the quantum realm plays by different rules. Here, there's a non-zero probability that the particle's wave function, the mathematical description of the particle's state, extends beyond the barrier. In other words, even when a particle doesn't possess enough energy to overcome the barrier, there's a chance it will be found on the other side, as if it has tunneled through. This is quantum tunneling, a concept that challenges our classical intuition but is a well-established and experimentally verified aspect of quantum mechanics. Does this seem a bit complex? Don't worry, we'll break it down for you. To understand quantum tunneling, we need to look at the Schrödinger equation. This equation, named after the physicist Erwin Schrödinger, sits at the heart of quantum mechanics. It's a mathematical model that describes how quantum systems evolve over time. But to truly appreciate its significance, we need to delve into a bit of quantum weirdness. Imagine a particle approaching an energy barrier. In the classical world, if this particle doesn't have enough energy, it simply can't cross the barrier. It's like trying to jump a wall without having enough strength. It just won't happen. But in the quantum realm, things are a bit different. Here, particles exhibit wave-particle duality. They can behave both as particles and waves. In the context of our energy barrier, this means that the particle doesn't just stop at the barrier. Instead, its wave function, a mathematical function that describes the quantum state of the particle, can extend beyond the barrier. Now, the wave function is not just some abstract concept, it has a physical interpretation. It represents the probability amplitude of finding a particle at a particular position. So if the wave function extends beyond the barrier, this means there's a non-zero probability of finding the particle on the other side of the barrier, even if, classically, it doesn't have enough energy to get there. This is what we call quantum tunneling. The particle, in a sense, tunnels through the barrier, appearing on the other side, a feat that would be impossible in our everyday world, but is a routine occurrence in the microscopic realm of quantum mechanics. The Schrödinger equation governs this behavior. It tells us how the wave function changes with time, and thus how the probabilities of finding the particle in different places evolve. In essence, the Schrödinger equation is the rulebook for quantum tunneling. So even when it seems impossible, the quantum world makes it possible for a particle to be on the other side of a barrier. This is the wonder and the weirdness of quantum mechanics, a field that continually challenges our intuition and reshapes our understanding of the universe. You might be wondering, where does quantum tunneling occur? Well, it's not just confined to the realm of tiny particles in a lab. Quantum tunneling plays a vital role in various natural processes. For instance, it's a fundamental aspect of radioactive decay. In this case, particles tunnel out of a nucleus, even though they don't possess enough energy to overcome the barrier in a classical sense. It's like being in a locked room without a key, but still finding a way out. The particle, say a neutron or alpha particle, is trapped within the nucleus by a potential energy barrier. This barrier is formed by the strong nuclear forces that hold the nucleus together. The particle doesn't have enough energy to climb over this barrier, so classically it should remain trapped inside the nucleus indefinitely. However, quantum mechanics allows for a different outcome. The particle's wave function can extend beyond the barrier, and as a result, there's a non-zero probability that the particle will be found on the other side. This is quantum tunneling, and thus the particle escapes the nucleus, leading to radioactive decay. This phenomenon is not just limited to radioactive decay. Quantum tunneling also plays a crucial role in the sun's energy production process. The temperatures and pressures in the sun's core aren't sufficient to overcome the Coulomb barrier between two protons. But thanks to quantum tunneling, these protons can get close enough to each other for the strong nuclear force to take over, leading to nuclear fusion and the release of vast amounts of energy that powers our sun. So, as mind-bending as it may seem, quantum tunneling is not just a quirky aspect of quantum theory. It's a fundamental process that occurs in nature and is responsible for some of the most significant phenomena we observe, from the radioactive decay that gives us insight into the age of our planet to the nuclear fusion that powers our sun. Nature has its ways of using quantum mechanics, doesn't it? From the natural world to our technological devices, quantum tunneling is everywhere. Its influence reaches even into the heart of our everyday gadgets. Let's take a closer look at semiconductor devices, such as transistors. In these devices, thin barriers separate different regions. Now, you'd think that an electron, behaving as a particle, wouldn't have enough energy to cross these barriers. But remember, electrons aren't just particles, they're also waves. So, in the quantum realm, these electrons can simply tunnel through the barriers as if they weren't even there. This tunneling effect is far from random. In fact, it's this very phenomenon that governs the behavior of these devices. Without quantum tunneling, our transistors wouldn't function as they do, and by extension, the digital world as we know it would look quite different. Quantum tunneling, though it challenges our classical intuition, is a well-established and experimentally verified aspect of quantum mechanics. So there you have it, a brief exploration into the fascinating world of quantum tunneling. This phenomenon, a fundamental aspect of the quantum world, is not just intriguing but also crucial in many natural processes. It's the force behind radioactive decay, where particles, defying classical physics, tunnel out of a nucleus. We've also seen how quantum tunneling plays a key role in technology. In semiconductor devices like transistors, electrons tunnel through thin barriers, thereby influencing the device's behavior. It's important to remember that the Schrödinger equation governs this behavior. It describes the non-zero probability that a particle's wave function extends beyond an energy barrier, even when the particle doesn't have the classical energy to surpass it. While quantum tunneling challenges our classical intuition, it's a well-established and experimentally verified aspect of quantum mechanics. Quantum tunneling truly shows us that in the quantum world, the impossible becomes possible.